This next presentation involves our next technique of integration. And what we want to do is use trigonometric substitutions to solve certain kinds of integrals. And let me show you by way of an example of why we would even care about this. Consider this integral, gang, okay? Notice that the outside is the derivative of the inside, okay? So this is a special case of the chain rule. We can either solve this by our experiences and just read off the answer, or we can just use a simple substitution. But otherwise, this is a fairly routine integral for us at this point. What makes it work is the presence of the 2x out in front, okay? In other words, the derivative of the inside is essentially on the outside, we're just off by a factor of -1. But what would happen if the x wasn't there? For example, see, now you don't have a chain rule anymore. However, there's a very clever method of solution for this. Okay, it's a kind of substitution. It's not U substitution like we learned early on, okay, but it's another kind of substitution where we let x equal the sine of the angle theta. So that when you take the differential of both sides of that equation, we get this. So why would we do it? Well, look what happens upon substitution, gang. Watch this. Replace the letter x with the sine of theta. Replace the differential of x with cosine of theta d theta. Notice that underneath the square root symbol, you've got the fundamental identity 1 minus the sine squared. Oops, hold on. I got ahead of myself. Right, and when you simplify that, right, the square root of the cosine squared is just the cosine. As long as the angle is in quadrants 1 or 4, remember, you got to be careful, right? You got the square root of a square underneath. You've got to make sure that you're going to retain a positive value when you take the principal square root. Cosine is positive in quadrants 1 and 4. But if we make that assumption that that's going to be the case, then this whole thing reduces down to just the cosine. Times the one that's there already gives us cosine squared. And now we can evaluate this. We see that the cosine has an even power, so we use the half angle identity. Okay, so notice what was the point of the whole substitution? Well, what, gang, in your mind, what's causing the problem in the original integral? What's the problem here? Yeah, it's the presence of the square root symbol. That's messing everything up. But with this trigonometric substitution, you know what it allowed us to do? It allowed us to algebraically eliminate the square root symbol, and then we could proceed on our way. Okay, we had an obstacle. We used a little bit of trigonometry, got over the obstacle, the hurdle, if you will, and it allowed us to continue and actually come up with an anti. Now, look, you're not finished. I should say that right now, right? We began the problem in x's. You have to finish that way, right? But the big idea here is that with a simple trigonometric substitution, we were able to eliminate the presence of the square root symbol. Okay, now here's how you go back, okay? I'm going to use a different color here. Use right triangle trigonometry. Okay, notice from your original substitution, the sine of theta is equal to x over 1. Well, you remember from trigonometry, the sine is the opposite over the hypotenuse. So I can use that substitution to label my triangle. By the Pythagorean theorem, I get the third side, okay? All right, now come over to our antiderivative, our preliminary form. And I'm going to replace this theta by using the original substitution. If x equals the sine of theta, then theta is equal to the inverse sine of x. Okay, but what to do about the sine of 2 theta? Well, getting the sine of 2 theta, right in the red triangle to the left, we have our triangle in terms of the angle theta, not 2 theta. So I'm going to need a trig identity here. Let me remind you, okay? The double angle formula for the sine says this. All right, so I'm going to use exactly that right here. Now it's kind of poor form to be mixing the x's and the thetas like this, but bear with me again, we're going to get there. Notice that the 1/2 and the 2 will cancel, but the sine of theta, remember, that's x. From the red triangle, the cosine of theta is the adjacent over the hypotenuse, or just simply the square root of 1 minus x squared divided by 1 plus c. Okay, it's not a routine problem, to be sure. The integral itself, it seems so unassuming, didn't it? Who knew that that square root symbol would cause so much trouble? But a simple trigonometric substitution allowed us to get past the hurdle, which was the square root symbol, okay, and kind of proceed on our way. All right, like I said, I said it before and I'll say it again, we recycle everything in this class, calculus 2, right? Trigonometry, algebra, the whole thing. Now, what I did was I made a little table for us right here, okay? If the integrand contains any one of these 3 forms, these are the 3 substitutions that we will make, okay? And notice this, kids, notice this. These right here, right, this corresponds to quadrants 1 and 4 for the reasons that we discussed earlier, right? That's the square root of the cosine squared has to return something positive because we're talking about the principal square root. Same here, this is quadrant 1 and 4, quadrants 1 and 4, okay? And then of course, these right here, this is quadrant 1, quadrant 3, okay? So those are the substitutions you're gonna wanna make if your integrand contains any one of these 3, okay? Let's try another one. Okay, now notice that this one has this form. Okay, so it looks like we're going to be making a trigonometric substitution that involves the sine. Mind you, again, the letter A represents a constant, okay, in all 3 of those definitions there. All right, let's see, what should we use? Well, how about this? Let's let x equal 2/3 sine theta. And why? Well, let me show you, right? If I square this, x squared is going to equal 4/9 times the sine squared of theta, correct? And you've got a 9 right here. When I multiply my x squared by that 9, it will cancel with this 9, okay, right here. All right, so sometimes you got to be a little bit clever. All right, let me clean that up. All right, so there's my dx, and then everything into the integral symbol, or into the integral, excuse me. and then we simplify. Oops, that was a 9, wasn't it? Sorry about that. And then notice that right here, all of this becomes 4 cosine squared. And when we take the principal square root of that, with the assumption that the angle is in either quadrant 1 or 4, okay, then we can simplify and get the following. Like the previous example, now we've got a power of the cosine that is even, and so that means we're going to have to use the half angle identity. Okay. In a similar way, I'm going to rewrite the sine of 2 theta with the double angle formula for the sine, like we saw in the previous example. All right, now we have to return back to the x's. So that's where we use our little red right triangle. Let me go back up here. And to label it, gang, I'm going to direct you back to our original substitution, this one right here. Okay. Note from that equation that 3x over 2 is equal to the sine of theta. Okay, 3x over 2 is equal to the sine of theta. And so while I label my triangle with the idea that the sine is the opposite over the hypotenuse, I get the following. And if I solve for the third side, I'll get the expression square root of 4 minus 9x squared using the Pythagorean theorem. All right, so according to our work here, I'll replace theta with the inverse sine of x, or the the inverse sine of 3x over 2. Here, the 2 and the 2 will cancel. The sine of theta is 3x over 2. And the cosine of theta is square root of 4 minus 9x squared, all from the red triangle. Okay, it's pretty involved, isn't it? Yeah, it is. Like I said before, it is not a routine problem. Okay, it's not a, kind of have to keep your wits about you. All right, now for this one, it has the expression x squared plus 1. There's no square root symbol in it, though. Okay, there's no square root symbol in it. However, gang, the expression on the inside of the parentheses, you know what it does? It reminds me, let me go back up to my little table, my makeshift table, right here. You know what? It reminds me a little bit of this one. So I think I'm going to make the substitution x is equal to the tangent of theta, where a takes the place of 1. Let's try it. And you know what? If it doesn't work, we'll try something else. All right, so our integral becomes the following. All right, how's that look? Now the tangent squared plus 1, that's the fundamental identity, right? That's the secant squared. And when you simplify that, okay, right? Because secant squared over secant to the fourth is 1 over the secant squared, which is cosine squared. So we have our fundamental identity. I'm sorry, we have the power of the cosine is even, so we're going to use the half angle identity again. Read off your antiderivatives. And then convert back to the x's. Double angle formula, huh? Okay. Now, from my original substitution, I know that the tangent of theta is x over 1. From trigonometry, that tangent is the opposite over the adjacent. And so therefore, by the Pythagorean theorem, we know the hypotenuse will be the square root of x squared plus 1. So down here, replace theta with the inverse tangent of x. Cancel the 2's. The sine of theta is the opposite over the hypotenuse. The cosine of theta is the adjacent over the hypotenuse. Pretty clever, huh? Now here we have a definite integral, okay? We have the presence of the square root of x squared plus 1, and the x squared plus 1 suggests a tangent substitution like the previous problem. Let's proceed with that. Okay, so x is equal to the tangent of theta. Mindful that the angle has to be in either quadrants 1 or 4. So our integral is going to look like this so far. Okay, so far so good. Now I'd like to also convert over the limits of integration, right? Currently, again, we have x equals 0 to x equals 1, correct? Now I can use my original substitution to figure out what my theta limit should be. All right, so for x is equal to 0, I'm going to have 0 equals the tangent of theta. And so that tells me that theta must be 0. For x is equal to 1, The tangent of theta equals 1, so theta must equal pi over 4. So now we've converted the entire integral over to thetas. Now notice also, gang, the tangent squared plus 1 is the secant squared. And when I take the principal square root of the secant squared, I just get the secant times the 2 that are there already. Okay, now look at that. That's one of the 2 special integrals that we discussed in a previous lecture, the integral of the secant cube. Now, the nice thing about converting the limits of integration over to thetas, gang, is that you don't have to use the little red right triangle to convert back to the x's. There's no reason for it, okay? Everything is in terms of theta, including the limits. So all we have to do is use the fundamental theorem and input the limits directly. Okay, and then the rest is just simply figuring out what this value is. I think we can get a pretty good head start on figuring that out without a calculator, gang, because we know that the tangent of 0 is equal to 0. So that means that this whole term right here is out. Okay, also, and same thing here, right? This is a 0. The secant of 0 is 1. So this entire expression right here is equal to 1, but the logarithm of 1 is equal to 0. So the whole second term drops out as well. All that's left is the first term. Actually, the first 2 terms. Oops. Okay, to get our final answer.